In the vast expanse of the cosmos, stars live extraordinary lives. These luminous giants burn for millions or even billions of years. But every star must eventually meet its end. For the most massive stars, this end is both spectacular and transformative. A supernova explosion that leaves behind one of the universe's most mysterious creations, a neutron star. When a star exhausts the nuclear fuel in its core, gravity takes over. For stars more than 8 times the mass of the Sun, this collapse is catastrophic. The core compresses under its own weight, and temperatures soar to billions of degrees. In this violent process, the outer layers of the star are blasted into space in a supernova. Meanwhile, the core is left behind, transformed into an incredibly dense object, a neutron star. What makes neutron stars so extraordinary is their sheer density. Imagine compressing the entire human population into the size of a sugar cube. That's the level of density we're talking about. A teaspoon of neutron star material would weigh around 1 billion tons on Earth. To put it another way, a neutron star packs the mass of 1 or 2 suns into a sphere only about 20 kilometers across, roughly the size of a city. This unimaginable density is a direct result of the extreme forces at play during the collapse. Neutron stars are made almost entirely of neutrons, subatomic particles with no electric charge. During the collapse, protons and electrons in the star's core are squeezed together so tightly that they merge into neutrons. This process halts the collapse as neutrons resist being compressed further, a phenomenon known as neutron degeneracy pressure. It's this balance between gravity and neutron pressure that allows the star to stabilize. But the wonders of neutron stars don't stop there. These objects also have incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields are so powerful that they can warp the very structure of atoms and emit intense beams of electromagnetic radiation. Neutron stars are also incredibly fast rotators. When a massive star collapses into such a small space, it spins faster, much like a figure skater pulling in their arms during a spin. Some neutron stars, known as pulsars, rotate hundreds of times per second, emitting beams of radiation from their magnetic poles. These beams sweep across space like a cosmic lighthouse, and when they cross Earth, we detect them as pulses of radio waves, X-rays, or even gamma rays. Pulsars are not only fascinating objects, but also valuable tools for scientists. Their precise pulses make them excellent cosmic clocks. In fact, pulsars have been used to test Einstein's theory of general relativity, map the galaxy, and even search for gravitational waves. Among neutron stars, one type stands out for its extreme characteristics: the magnetar. Magnetars are neutron stars with magnetic fields up to 1,000 times stronger than those of typical neutron stars. These fields are so intense that they can distort the shapes of atoms and unleash powerful bursts of X-rays and gamma rays. A single burst from a magnetar could disrupt satellites and even disable electrical grids on Earth, even from thousands of light years away. The mysteries of neutron stars don't end with pulsars and magnetars. Some scientists hypothesize the existence of quark stars, objects that go even beyond neutron stars in density. In these theoretical stars, the neutrons themselves are broken down into their constituent parts, quarks. While quark stars remain speculative, they offer a tantalizing glimpse into the possibilities of matter under extreme conditions. Neutron stars aren't just isolated cosmic wonders, they play an important role in the universe. When 2 neutron stars collide, the results are both spectacular and scientifically invaluable. These collisions release enormous amounts of energy, producing gravitational waves, ripples in space-time that can be detected here on Earth. In addition, these mergers create heavy elements like gold and platinum, seeding the universe with the building blocks of planets, life, and even jewelry. One of the most famous observations of a neutron star collision occurred in 2017, when scientists detected gravitational waves from 2 merging neutron stars. This event, known as GW 170817, marked the first time gravitational waves and electromagnetic radiation from the same event were observed, opening a new era in multi-messenger astronomy. From this one event, researchers learned about the physics of extreme gravity, the origin of heavy elements, and the processes that shape the universe. Neutron stars push the boundaries of our understanding of physics. They represent the ultimate interplay between gravity, quantum mechanics, and nuclear physics. By studying them, scientists gain insights into the fundamental forces that govern the cosmos, from the tiniest scales of subatomic particles to the vastness of galaxies. In the end, neutron stars remind us of the universe's extremes. Born from the death of stars, they are among the most extraordinary objects in existence. Their density, magnetism, and sheer power make them cosmic laboratories, offering clues to some of the deepest mysteries of the universe. From pulsars ticking like celestial clocks to magnetars unleashing bursts of energy, neutron stars are not just remnants of stellar death, they are a testament to the incredible forces that shape our universe. So the next time you look up at the night sky, remember that hidden among the stars are these cosmic titans, silently spinning, emitting light, and telling the story of the universe's most extreme phenomena.